In order to get the most out of the fourth axis machining module in Gearotic Thoughts, it's best that a user have an understanding of exactly how tangential shaving works as a method of machining a gear. So we're going to do a very quick tutorial on how exactly that works, because I know that there are some out there who really don't understand. As you can see, I have on the screen a picture of a spur gear, and we have two circles on it. One is the pitch circle, the one I just highlighted here, and this is the point at which two gears which are meshing will be touching. If I wanted to mesh a gear with this, I simply have to make sure that its pitch circle touches the pitch circle of the mating gear, and the two of them will mate, will mesh properly. So let's get rid of that circle. I think that most people are used to seeing the pitch circle and know what it is. We're left with this circle, which is placed at the base. This is a base circle, and it's the circle which is probably most important to the generation of a gear, and yet understood by fewer people. The base circle is the main mathematical instrument used to generate the involute curves, which are primary to the teeth, of course, on involute teeth. To create an involute tooth on a gear, we take the base circle and we virtually unwind a string from this circle, and that string, as it unwinds, will create an involute tooth such as we see here. As you can see, if I unwind the string from this base circle, as I get it up to this point, I have so far drawn this area of the involute curve, and as I continue to unwind from the base circle, the point will move further and further up, drawing our involute shape. In order to do the other side of the tooth, of course, we'll unwrap from the other direction on our base circle. The base circle is also important if we want to figure out how to machine this gear to get nice involute shapes on its teeth without having a bit which is shaped like the teeth. Incidentally, on our DXFs now, you will see this shape to the right of the gear. One user has asked me what this floating ghost tooth is for. This ghost tooth is actually a shape that you can use to create a fly cutting bit to be the exact correct shape in order to cut these gears very quickly. And we'll talk about fly cutting the gears very shortly when we get back into Gearotic. Until then, we don't need to worry about this ghost tooth anymore. So we'll get rid of it. So imagine with me, if you would, we have a tool bit which we'll represent as this small rectangle that I've just placed on the screen. And as you can see, I have put it directly at 0, with one side of it touching 0. And I'm going to rotate our gear so that it rotates up and just touches that bit. Now, as you can see, if I rotate our gear so that our involute tooth just touches that tool, this is the point at which we would be removing string, unwinding string from the base in order to create this involute curve. And involute theory tells us that this tool, if we move it the exact distance of the length of that string that we're unwinding, will always be tangent to the tooth. Let me explain that term, tangent to the tooth, for a second. Zooming in on this tooth, we can see that I'm picking a point right here on the curve just as a point of reference, just as an example. The line which comes off so that there's as many points below the line as there is on the other side below the line, so that the angles are identical between above and below the line, that would be considered its tangent point. Now, when we rotate the gear enough that that tangent point is vertical, that's the involution point of that gear. That is the point, if we measure the length of the string that we would have had the string been unwound to this exact point and moved the tool to the left by that exact amount, the two of them should be meeting up at the perfect tangent point. For example, like this. Okay, so here I have moved the tool to the left by the length of our string, which would have been unwinding to create the involute point. And now if we zoom in on our tooth, we can see that our tool is actually shaving the tooth right at that point. Let's erase our test line, and you can see that our tool is now in the perfect position to shave this tooth And if we do this at enough points throughout the rotation of this tooth, typically in gearotic motion we do 8 points evenly up the length of the tooth, and we find that tangent point for each position on the tooth, and we shave it with the edge of the tool, we will have created an involute flank. We then repeat the process with the other side, and that is essentially the process of involute shaving. Here would be another position, for example, that we could touch. The tool is now tangent to the tooth and will shave from this portion upward. If you were picturing us machining this tooth, you can see that as we move along, going higher and higher up the tooth, and the tool is moving further and further to the left, we'll be shaving an ever decreasing amount of this tooth, and in the end we're going to leave only that involute flank. Here's another spot. Now this is the position most written to me about by gearotic motion users. They would be cutting a gear, and what they would find in the end is that on their final passes the tool would not be touching the edge of the gear. It would in fact be off in space somewhere out here, for example, and they would be wondering why I put in a pass where the tool is not even touching the edge of the tooth. Things like this would happen because of inconsistencies in the math in the user's own setup. For example, the blank for this gear should be exactly a radius of 45 millimeters by definition. This was a 90 millimeter wide gear. However, if the tool was not zeroed exactly at 45 millimeters, even being 1 millimeter less, 1 millimeter closer to the center of this gear, could make the math point this tool 2 or 3 millimeters to the side. So it wasn't an uncommon complaint that someone would say, I have been cutting my gear and the tooth is not touching the tool on the final pass. And this was always an indication of inaccuracy in setup. So if you find this happening to you, look very carefully to make sure that you have specified the correct diameter gear, you have cut a blank of the right size, and you have zeroed the tool at the correct position, which is the point where my mouse is pointing right now, the very dead top center of the gear, as we'll see in examples coming up very shortly. You'll notice throughout this that I never move the tool up or down. I simply move it back and forth and rotate the gear to match the tool. This is all part of the mathematics of the involute curve. We are guaranteed to get a nice tangential fit, provided I never move the tool up or down from its location. I follow its base curve to the left by the amount of the unwound string, while rotating in the opposite direction by the amount of angular relationship, and this will always generate the proper positions for a tangential shave. Now the reason that this is important for you to know is that in future, in actually this coming release of Gearotic Thoughts, you are no longer limited to involute gears. You can do epicycloidal gears, you can do timing pulleys, you can even do bicycle sprockets, all on the fourth axis. But there are things that you're going to have to consider and things that you're going to have to look at due to limitations in the fact that if you don't have a base circle or an involute curve, the mathematics is not as straightforward and cut and dried as it is for involute math. In an epicycloidal, it would be possible to rewrite the relationship between the tool travel and the flank of the tooth to be sinusoidal rather than involute, but that would not solve the problem when it came to sprockets and timing gears, which follow some pretty strange math, and oftentimes they're simply random concatenations of arcs, which would make it almost impossible for me to come up with an algorithm which can reliably cut them on a fourth axis. I think that we've come up with a pretty good solution though, and we'll discuss that now that we're going into Gearotic Thoughts to look at the new fourth axis module. I just thought it was important for people to realize exactly what tangential shaving is, because it will become important as of this release of Gearotic Thoughts. And I did promise this would be a brief tutorial, so that's it for this tutorial.
Alright, so hopefully I didn't bore you too much with that brief introduction to tangential. And I did leave a title clip so that you can fast forward through it in future. Here on the screen we have 6 objects which I have randomly created. You can see we have a herringbone, a knuckle gear, there's a sprocket, there's an HTD14 pulley in the center there. We have an ordinary spur gear, and we have a helical gear. So we have kind of one example of several different types that we can play with CNC. The CNC module is designed to be quickly entered and exited if you're playing with a mechanism. So let's assume that these gears I have on the screen just happen to be the mechanism I'm playing with, and I decide that I wish to run a machining set on some of them or all of them. The CNC button up here in the corner, we simply click that and we'll go to a CNC screen on the bottom here. It says G-code processing. And it shows us a good many selections, much more than we've had, and we'll explain all those. The screen, you'll notice, is still showing me my 6 objects, and this is because I have not yet selected anything to be machined. A message passed by on the screen saying select object when I press CNC. You may not have seen it. System messages last for about 4 or 5 seconds and roll off of the screen so that they're not constantly bothering you. So at this point the system is waiting for me to click on an item. So let's click on the spur gear over here on the project screen. And when I do, the screen clicks to a display showing a T-slot table with a piece of stock on it. And you can press the button down here from object to get a new piece of stock size if you wish. It's automatically done as it loads anyways. To just show you a typical piece of stock. You'll notice we have a machining bit positioned at the lower right corner of this block. And if we hit the regen button or generate paths button down here in the bottom, a toolpath will appear on the screen. And the toolpath will follow the parameters of what you have entered on the parameters box down below here. Similar to Gearotic motion, several of these settings may or may not function for a given mode. So each mode will have a different series of settings which affect that mode, and in the end they will light up green for the ones which affect your current modality of machining. Currently we have 2.5D profiling turned on, and as you can see on the screen, that is what we're getting. You can see that the tool is zeroed down in the bottom left-hand corner of the screen, and that corresponds with an origin box down here in the settings. This means that all numbers put out to the G-code file will be referenced with 00 being in the bottom left-hand corner. This was a request from a few people in Gearotic motion who wished to be able to move it around. By clicking on the origins down in the origin box and then regenerating, you can see now my tool is in the center of the screen. This is the new 00 position, and you can select any of them in the origin box. The regeneration will be automatic very shortly in the future, but at the moment when something doesn't look right, use your regeneration button to regen things. And if they are correct, it should look exactly as you would expect it to look on your machine. At the moment, you can see my tool is sitting up off of the stock a small amount, and that's the safe Z setting down here in the parameters. If I change safe Z, for example, to 5 millimeters and hit regenerate, you can see that things have moved. The rapids have moved higher above the material. The tool has also moved higher above the material, and the tool path, I have to hit regen a couple times, and now the tool path starts from the tool. This will tell you that everything is ready to go. Some things become obvious now that we can see a tool path. Unlike in Gearotic motion, you kind of had to take your chances that you had things set properly and it would give you a proper path. Here you no longer have to do that. For example, on this cut, you can see it's going to a depth that I have specified in my final depth. It's doing so in a number of passes equal to my setting for depth per pass down here. But you can see it did not drill the center hole, the shaft hole. A quick look to the diameter of the tool at 2 millimeters will tell you the tool is too large to fit into that hole. If we were to lower the size of the tool bit to 1 millimeter, for example, and hit regenerate. Now you can see I have a shaft hole being drilled. So you won't necessarily get an error telling you that a particular piece will not be machined due to a tool bit size error. That's considered a feature. You could have a gear with some very fine, finicky spokes. The system will pocket out or will contour out what it can. It will ignore what it cannot have. This means is if you were to put a gear on here with spokes which were meant for a laser cutter and therefore have some very highly intricate spoking, you could still machine it. You just would not get contours cutting out the complex bits. So that's considered a feature, that it's automatically discarding anything that it cannot do. You can see that it is intelligent enough to know that shaft holes should be drilled first, spokes should come out second, and finally the outside shape of the involutes will be cut. Because this isn't a typical CAD program, I was free to do several things because I knew things like orders and so on. This is all making it easier on you. I don't have to make you select a lot of things that you probably don't need to select. You will find a setting in here, for example, for final pass. That's not something that's needed when you're contouring, but if you were to put final pass, you'll find suddenly a final tool path being generated of a small size. Let me give it a final pass of 0.5 millimeters here. Hit a regen, and you can see another path has just appeared, so that our final path is only half a millimeter in this case. Again, normally you'll leave that at 0 until we have the capability of pocketing things, which is where that can become important to give you a nice smooth finish. Set your spindle speed, set your feed rate. The system will give you an approximate machining time and tell you the full length of the path. That will be tweaked over time. Incidentally, on bugs, you will probably find a million things in here which act strange or allow you to make impossible tool paths. We'll tighten this up, obviously, as time goes by, but for an initial release, you'll find that you haven't been limited very much, and you can do some pretty strange things in here. So always look to your path to make sure it looks correct to you, that things look as you would expect them to look. Like, for example, on this gear, I'm not cutting through the material, so I'm not actually going to get a gear out. So it would be best if I changed my final depth to the real depth of the gear, which I happen to know is 20. So there we would get a proper cut right through the gear if I go to 20 millimeters full depth. Just a note on colors here. If you push the options button up in the corner, you can see that we have rapid, plunge, and feed colors that you can select. If you just hit like the feed color, for example, and select a color, the feed will, on the next regen, update to the new color. You're free to choose whatever colors you like. In fact, if someone finds a really good color scheme, I'd like you to post it on the forum if you would, and perhaps we can adopt it for everyone. I'm a bit colorblind, I admit that up front, so you may or may not like some of the colors I tend to come up with over time. So again, keep in mind that you can change almost all the colors in the program for the most part, and I'll give you access to other colors if you find that you would like to have them. The T-slot bed and so on is just a construct of mine in order to keep things clear in your head. I've decided to adopt a system where the screen is always X in the bottom, Y going up, which means that when you use your smiley face up here to look straight into a program, you'll know that X is the horizontal direction and Y is always the vertical. This will be also true of the G-code. And you need to know that, and that'll become apparent to you in a few minutes. Also, for the 2.5D machining, some of the settings you don't need at the moment, such as step over, that's really used when pocketing operations that we may need to use in upcoming ratcheting and cycloidic planetaries and so on. Your final depth and depth per pass are pretty obvious. Spindle speed, feed rate, final pass. Your safe height is the same as before. Basically, it's the height that you will retract out of material. You do have a plunge speed, and that's about all that you really need to know for 2.5D machining. It's pretty simple. If you hit the post button, the code will be put out into your project file, and it will ask you for a project file if you don't already have one selected. Otherwise, just putting post button, you will get a message that the file post is in progress. You'll then get another message saying it has completed successfully. At that point, you know that the file is out there. It's very fast. This is all new code. It doesn't rely on other people's libraries. So it's very efficient and it's very quick. And hopefully it's a lot smarter than some of the code that we've used. There are bugs in the program that you're going to see occasionally. Such as here, you can see I have 1% J minutes for the approximate machining time. For some reason, it could not, on that pass, figure out what my possible machining time was for this job. Little bugs like that will be fixed up over time. Now, in addition to 2.5D machining for that spur gear, obviously we could go to 4th axis. Along the bottom row here, we have a machining modality. We can select 2.5D profiling, 3D waterline, which is not yet available to you. If you select it, the system will deselect it again and give you a warning saying incompatible modality selected. You have 4th axis and sliced 3D printing machining. The sliced 3D printing is the same as 3D waterline. It is at this moment turned off completely. The 4th axis button, however, when selected, will put you into a 4th axis display. And you remember what I said earlier, when you press the center button to look down on your object, and you might have to press it twice because it goes upside down if you press it while it's pointing directly out. So make sure that you're looking at it the right way. This is the right way. X is across the horizontal, with X++ being to the right and X-, to the left. So in my system, the 4th axis is pointing along the X-axis. I realize that some of you do not have a system where it is in that orientation, and if we go up to the options again, you will see a 4th axis setup with selections for which axes your chuck on the 4th axis is pointing on. For example, if I was to select Y++ and then do a regen of the system, you'll see now that the 4th axis is at the bottom of my screen, and the gear is being cut in the Y++ direction. These settings are all necessary, of course, so that you can get the proper G code out for your machine. So make sure that you have set up your 4th axis to be facing in the direction that your system has, and the benefit here is it really should look like what's on the screen. Not physically, but metaphorically at least. You can see we just have a fake transparent 4th axis with a shaft and a little stepper motor on the back, which supposedly drives this thing around. I'm going to change my orientation so that we're looking straight into the chuck at the moment along the X++ axis. You'll notice we're actually tilted over so the table is over, but that's another issue that will be dealt with over time. So looking at it in this orientation, we're looking straight at our gear, and we can see our toolpath quite nicely. You can see where the tool is zeroed is right on the disc of our blank at the very top of the disc, dead center. That will be the 0 point for all future toolpaths. That's the point where you will want to simply touch off to zero the machine before running the code. Now this is where it becomes important that you understand a little bit about tangential machining and about how I'm displaying this toolpath. 4th axis toolpaths are very hard to display. Typically, if I was to display them for you exactly what was going to happen, what you would see on a typical XY system is simply the tool running straight back and forth in the X while the rotary rotates. This means that all the motions, all the toolpath display would be up here at the top, and it would just be a mess of lines and arcs, and you wouldn't be able to tell what's going on. So for my display, I've taken the liberty of taking the toolpath and rotating it around the disk instead of simply assuming that the disk will rotate into the toolpath. So in other words, the graphics are not really a visual representation of where your tool is going. That should be obvious because you cannot have a tool in a typical system coming in from the bottom and so on. This leads to strange arcs on the screen and such, so that if you, for example, take a look at this start waveform, this is the start cut for this tooth. So you can see the tool is going to lift up in the Z. Z at the moment is to my left. It's going to lift up, position itself, and come down and start to cut these tangents. Now this may not look immediately obvious to you what it's doing. If I rotate this slightly, you can now see that actually the tool is picking tangent points and cutting its way up the slopes of those teeth. Now, that is what shapes the involutes flanks of all these teeth as it goes around. These strange arcs are due to the fact that the tool may be staying in space as the blank rotates, which lowers its effective height to the blank, and it creates strange looking arcs and so on, but these are all actually quite correct. Now, if you should inspect all toolpaths that you're going to get to see if anything looks strange, and you want to be familiar with what would be strange. This is actually a pretty good toolpath, but there's something visibly missing, and that is roots. We don't appear to have any rooting to remove the start material. If you press regen to see why, if there's an error, it should appear at the top of the screen, and in this case when I press it, the error says too many passes, diameter of bit too small for roots. Well, that's true. I have a 1mm bit, and if I was cutting with a 50% step over to root out with a depth per pass of 1, this is going to make an incredible amount of tool paths. So rather than create a multi-megabyte file, the system is warning you that that's simply too small of a bit to do this tooth with if you want to get any clearance out of it. So let's move our bit up to a 4mm bit, which would be much more realistic. You can see our bit is now changed to a 4mm bit. The sizing is all proper. And now we have a stranger looking toolpath. Let's take a look at this dead on straight in, because without the parallax you can better see the toolpath. We actually have two toolpaths going on here. Down on the screen you can see under fourth axis we select a type of machining. At the moment we're on tangential bit. This is the typical GM style machining with the tangent on the side of the bit, and that's what we have used before, and it's likely what you will use the most now. Underneath at the bottom of it though, there's two check boxes. One is for rooting and one is for toothing. This can be thought of as similar to roughing and finishing in terms of 2.5D machining. If, for example, I turn off rooting, you'll see that now I only have my tangential paths. The blank is going to rotate and the tool is going to move over to the right position, which will create a positioning equal to all these points in 8 points going up. Now again, we said in the introduction to tangential machining we tend to pick a series of points. It was 8 in Gearotic motion, typically set to 8. You can see on the screen under parameters there is a box labeled segment fourth, and it's set to 9, and that tells us that we're getting 9 tool paths shaving the tooth. And if I just tilt the gear slightly, you can see all 9 tool paths. 1, 2, 3, 4, 5, 6, 7, 8, and the 9th. The 9th is right up at the tooth, so it's not actually cutting very much in this particular case. Where it cuts closest to the tooth will typically be determined by your segmentation and how deep the tooth is. In either event, this will give a pretty well-shaped involute from this program. So if we look at it straight in again to get rid of that parallax, you can see that we have our tangential. Now if I turn off the tangential and turn on rooting instead, here's our rooting path. Now the rooting is fairly simple. As you can see, it goes in one layer at a time, going deeper each time, clearing as much as it can as it goes down. If we then turn on the toothing will appear over it. This toolpath is actually not going deep enough, I think, to take care of that root, and I'll check that before I post this code for you. This appears to be giving me an offset at the bottom that it wasn't yesterday and shouldn't give. In any event, it is the combination of these two which will create the toolpath for each tooth to clear it out. I did have many requests in Gearotic that you could use maybe a bigger tool to do your rooting and a finer tool to do your toothing. And this is why you can turn off rooting or toothing. So what I could do is turn off toothing, leave it as a rooting path with one particular size of tool, and save that as an output file with post code. This will post a code label with a name of spur rough. If you then turned off rooting and turned on toothing and generated the toolpath, you would get a file called spur fine. And if you have them both on, you will get a file called spur rough fine, which tells you that one tool is doing both the finishing and the roughing both. Okay, in the previous, just a second ago, I had too large a tool diameter. You can see now if I shrink my tool diameter, I can now get to the root of the tooth, and that's something you're going to have to watch out for until we find a better way of navigating some of this. The problem is we are no longer doing these toolpaths by algorithm which looks at the parameters of a gear. We're actually using the profile of the tooth because that'll allow us to do epicycloidics as well as spur and timing gears and so on and so forth. Because of that, you have to be very careful that the toolpath you're cutting is appropriate for you. And in this case, when I had a 4mm tool, we were getting down to the root, but it was clipping on this curved trochoidal portion of the root, and since it has been instructed to never cut material which is not which is inside the gear, it simply would not go down to the bottom and do it. And this is why it's important that you verify your toolpaths by at least looking at them judiciously to see if you're actually getting what you expect. And if that tool is going to do the job. You can see when I take it down to a 2mm tool in this case, I get even more of a tool path and more of a clearing, and I begin to see the shape of that trochoidal root reflected in the shape of this bit. This kind of tells me right there that this, if I want a really fine resolution of the root, I would almost have to clear it with a 2mm or maybe 2.5mm bit. Anyway, this is one of the things that you should watch out for. As you can see, as I go up in diameter of the bit, my tangential points get further and further away from the actual tooth of the gear, which is as you would expect. If I bring it up to 4mm, for example, I'm going to turn off rooting because 4mm can't do the rooting. So if I generate on a 4, you can see that, again, we're 2mm now away from the edge of the gear points. I overlay this gear onto the blank to give you a better impression of how your toolpath matches up with your gear. I hope it's helpful in that respect. But another thing to watch out for is if we now raise our diameter up to 6mm, you can see the lines are getting very close together. At the point at which these lines touch or cross means you've got too large a bit. Eventually the system will use that information to warn you. But if I take it up to an 8mm bit, for example, we've now crossed paths. And just like crossing light beams in Ghostbusters or whatever, this is going to destroy your tooth. So make sure you never cross the beam. You want to take that down low enough so that there is a good separation between the two. And that's all you need to worry about. When it comes to rooting, take a look at it to make sure you're going low enough into your root. This obviously would not work. We're not getting anywhere close, so 4mm bit would not be able to cut this gear properly if I want to worry about where those teeth are. So I'm going to take that down to a 3mm bit, and that's much better. We're probably less than 1/4mm from the bottom of the actual root. Would probably do a pretty good clearing throughout, and is certainly worth a shot. Again, this is early days for this algorithm, so we're going to discover together what its limitations are. whenever you look at the final toolpath in various angles, you can see it gets pretty complicated looking. So you're really advised to take a look at it from the left or right and just see, does it make sense to you in that matrix? Don't worry about the sweep across. The system will take care of making sure that that is valid. All you really need to worry about is, does it look proper in its matrix? This is not always easy to do, I might add. This is a particularly easy one because it's simply a spur gear. But it's not always just a spur gear. But before we discuss that, let's take a look at another option. Besides tangential bit down here, we have tangential saw. This is meant for using a fly cutter. Some people's systems, the fly cutter sits to the side. And here the system will assume that this cutter is the thickness of the diameter setting of the tool. So it's simply assuming that the tool, which is a saw, is coming in sideways on the system, and the G-code which will be put out will be reflective of this setup where the saw is coming in, a slit saw is coming in from the side to cut the gear. Now another possibility you have, as we discussed in the introduction video, I do put out the tooth shape for every type of gear now. If you wanted to cut a fly cutter for a profile for that, you have two selections down below tangential saw. You have involute bit. This assumes that your bit, and I do not yet draw it as an involute. I probably will someday when I get time, but I don't want to waste development time on the little toys I'll do when we're all done. But as you can see, this toolpath now simply lowers gradually down through the tooth, doing pass after pass after pass. It would be finished within a few seconds. Probably take less than 30 seconds to cut the entire gear if you've got any speed to that involute bit. So this is why some people would prefer to use a fly cutting option. So this selection allows you to do that. And you also have involute saw, just in case you're using a slit saw that is involute shaped, or a fly cutter with involute teeth in it. You could use this to generate the G-code for you. And again, you can see its orientation. Remember again that if your orientation is not this, you can change it in the options menu to have the face of your chuck face in any direction that your system might have it in. Tangential bit will probably be the most used option for most people. So let's take a look at what happens. You're going to find that with the right selections, you'll get pretty much perfect involute teeth, just as before. Let's look at some of the other options, though. All you have to do to switch to another gear is your project screen is on the screen. Just go click on one of the other gears or one of the other objects. Let's click on the helical gear. We'll get a message on the screen asking us if we wish to change the object for G-code output. If you say no, we'll just stay where we are. If we say yes, we will switch to the helical gear that we had there. And as you can see, the path has already been generated for it. I do recommend you push regen anyways. You can see that the tool just repositioned itself, so something wasn't set proper. But now you can see that our code is helically shaped. And it gets a little harder for you to verify it because it's hard to find an angle at which things are no longer all complex due to parallax. And you can see, though, by looking at the toolpath from various sides, we are actually going quite a bit to one side of the gear, starting to sweep across to the other side of the gear, and we leave ourselves a fair amount of clearance on both sides. That clearance is set by a drop-down box beneath routing and toothing called clearance, and you can select up to 100% of your tool bit to step off to one side of or the other. This gives you room in case your gear is wobbling back and forth a little bit because you're not 100% centered. This could stop you from scraping the side of the gear. Hopefully you don't have any wobble, but if you did, this might help you. You're going to find that you don't have to be 100% dead accurate when you're cutting a gear. It's amazing the actual tolerances that are built into the system. But when you find, as in the video, that you're machining something and the tool is coming way over to the left and it's missing the blank entirely, that probably means that your setup is wrong. These tool paths, now that we're actually displaying them so that you can see them, actually provide quite a bit of information. In Mach 3, I was always very careful to keep the machine coordinate display away from all influences of the system so that it only counted actual pulses going to a stepper motor. I did that to ensure that I was always safety checked when I did further programming. Here I've done almost the same thing. The code which displays the fourth axis toolpaths has nothing to do with the code that generates the toolpath. So if a toolpath looks right, it probably is. If it looks wrong, it probably is. So it's certainly worth checking. But with helicals, you can usually tell if a helical path is correct, because if you tilt to a helical angle, which if you look at this area here now, you can see it looks like I have an involute tooth, an untouched involute tooth. If I just tilt it to the right angle, there's my involute tooth. It looks properly shaped, and that usually is your indicator that a helical gear is properly being cut. Because if you look at a helical gear blank straight in, just looking at the shape of the teeth that you get, what you will see is our teeth, which are not really a true spur gear tooth. They're too fat and just not the correct shape. It isn't until you look at them at the right angle that they begin to look like proper spur gears. So that's a helical gear, and should cut quite nicely. I have tested spurs this morning, but I have not yet tested helicals and so on, but I'm not seeing any errors. We also have herringbone gears. And if you look at a herringbone, you can see from above anyway the helical shaping. You can see the routing and so on, and the roots are pretty good, what we have selected and so on. The center, however, is not going to give you a nice sharp corner due to the roundness of your cutting bit, so you're probably going to end up having to put a herringbone onto your lathe and spinning down a little groove in the middle to take care of that sharpness. This is one reason that herringbones are a little bit hard to build. Personally, I prefer a knuckle gear. Let's take a look at a knuckle, although I will warn you, knuckles are the most complex of gears because they take a long time to generate their display lists. So expect to wait for up to 10 or 20 seconds for a knuckle gear to be fully created. Once it's created, it can display quickly and you can rotate and so on because it's in a display list. But generating that display list, I'm still working on doing that faster. A knuckle gear is rounded on the front and concaved onto the back of the next gear. This allows them to plug into each other, doing the job of a herringbone without being herringboned, meaning you don't have to turn it on a lathe. They should cut fairly quickly, even though they take a long time to generate in terms of G-code on or display on the screen. This toolpath is a very complex one because it has to arc and curvature every point to fit around that blank as it's going, and that's why it takes so long to generate. You'll notice that how busy the toolpath is. Some of that is due to my depth per pass here, where I'm the final depth setting under parameters is not used because it's going to go to the bottom root of the tooth no matter what, but your depth per pass is used. So if I increase that from 1 to 3, you'll see, and again, it takes a long time on a knuckle gear to generate, but now that I've selected 3, you can see that the toolpath is actually not as complex as what it was before. You can, by careful manipulation of the screen, you can kind of zoom in to see how complex things are. You can get a visual, and I'm not sure the video will do it for you, but by rotating slowly back and forth and so on, you tend to get a pretty good mental image of where everything is inside that tooth space and how it's missing the overlay profile, which shows you that the path is a good one. I'm hoping these displays go a long way to helping people visualize things that they couldn't necessarily visualize before. Let's take a look at an odd one, because here's an HTD14 pulley. There was no capability of doing this type of thing in Gearotic motion, and again, the problem results from the fact that these are not involute shapes, and in fact an HTD is a concatenation of arcs that don't necessarily make sense to each other. So I do give you the capability of cutting them, but the algorithm struggles, and as you can see, the algorithm is finding as many tangential points on this rather bulbous arc as it can to do the tangential runs. And I'm not so sure how that would work out. It will probably give you that bulb shape, but the routing is not going to be able to do a very good routing of this round area. So while a toolpath on an HTD such as this one could theoretically get you close to the shape you're looking for, I would expect that you would have to take a file to this and dress it up quite a bit to get what you're looking for. Now, that having been said, I have been asked by a great many people over time to allow this kind of thing so that you could at least rough something out to come close to a shape that you might need on a particular item. And it does make a great deal of sense. The best way, however, to do something like that would be to go to an involute bit selection. And now you can see that we're cutting the pulley quite nicely. Your responsibility, however, would be to make a cutter, which is the shape of one tooth of this pulley. That tooth shape is put out in the DXFs, so you can use the information from the DXFs to join or to make those shapes so that you can get a very nice, easy fly cutting operation done. And again, if you have a saw type or slit saw type cutter holder, you could go to this and do the exact same thing from the side on your particular system. Again, remember to tell the system which way you're actually facing with your fourth axis. Well, that's about it for this module. I hope you have fun playing with it. As I said, be careful with it. Make sure that it's giving you G-code that looks appropriate before you try to cut it, because a lot of it is not yet verified. I am verifying it as I go. Yesterday's gear worked out very well. The code is very efficient, very fast, and can cut gears in a much faster time than Gearotic Motion could. And as I say, it's early days, so it will grow in its complexity and its stability over time. So have fun with it. Till later.